Hello student, today I am going to discuss Avogadro Law, that is volume amount relationship. Last class I have discussed Charles law, Gay-Lussac law, Boyle's law also I have discussed. Now I am going to discuss Avogadro law, that is volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusions of Dalton's atomic theory and Gay-Lussac's law of combining volumes is now known as Avogadro's law. Okay, again you listen that conclusion of Dalton's atomic theory and Gay-Lussac's law of combining volumes, which is now known as Avogadro's law. It states that equal volume of all gases under the same condition of temperature and pressure contains equal number of molecules. This means that as long as the temperature and pressure remain constant, the volume depends upon a number of molecules of the gas, or in the other words, amount of the gas. Mathematically, we can write V is directly proportional to N, small n, where N is the number of molecules of the gas. Or if we will, this proportionality sign, if we will change to equality, then we can write V is equal to Kn, where K is a constant. The number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23. This is the number. It may be anything, maybe particles, maybe ion, maybe proton, neutron, electron, anything in this number, and is known as Avogadro constant, means 6.022 into 10 to the power 23 is called Avogadro constant. Now we will see that this is the same number which we came across last time what we have discussed. Now this is the same number. Then here Avogadro's law, simply mathematically you can tell V is directly proportional to N, that is the number of moles of the gas. Since volume of a gas is directly proportional to the number of moles, 1 mole of each gas at standard temperature and pressure, in short we are telling STP, will have same volume. At standard temperature and pressure will have same volume. Standard temperature and pressure means 273.15 Kelvin, that is also called 0 degree centigrade, and pressure is 1 bar, that is exactly 10 to the power 5 Pascal pressure. Okay, temperature is 273.15 K or 0 degree centigrade temperature, and pressure is 1 bar pressure, which is exactly 10 to the power 5 Pascal. These value approximate freezing temperature of water and atmospheric pressure at sea level. These values, what I told you, temperature and pressure, these values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gases is how much? Then this is very important things. 22.71098 liter per mole. This is the exactly. Simply we are telling by 22.4 liter. 22.4 liter at STP, but exactly that was that normal temperature NTP. Nowadays we are using the term STP. At STP, molar volume of an ideal gas or a combination of ideal gases is 22.71098 liter per mole. I want to tell you that some values, molar volumes in liter per mole of some gases at 273.5 Kelvin and 1 bar. Some gases I will tell. For argon, its value is 22.37. At STP I am talking about. At STP means when temperature is 273.15 K and pressure is 1 bar. That time argon, 1 mole of argon has 22.37 liter. Okay. And carbon dioxide 22.54. Nitrogen, which is also called dinitrogen, nitrogen gas 22.69. Dioxygen, which we are telling oxygen gas 22.69. Dihydrogen, what we are telling H2, that is 22.72. Ideal gas 22.71. Okay, this ideal gas volume we are considering as a standard. This I have told about the volume of 1 mole of some gases at STP means 273.15 Kelvin and 1 bar STP. Number of moles of a gas can be calculated. How will calculate? As follow. You can calculate as follow. It is very easy to calculate. A small n, what we are telling is number of moles. If we are knowing mass of the gas and if we are knowing molecular mass, then a small n is equal to m divided by capital M, where m is equal to mass of the gas under investigation and m is equal to molar mass means molecular weight. Then n you are knowing, n is equal to m small m divided by capital M means mass divided by molecular mass. Now we know that just now we have discussed V is directly proportional to N or V is equal to Kn according to Avogadro law. This is actually Avogadro law. V is equal to Kn and N is equal to M upon capital small m upon capital M. Then now you got the relation V is equal to K into M divided by M. K was already there, on the place of N you have written M small m divided by M. Now from this relation you can get the value of M also, capital M. Molecular mass you can calculate very easily because the relation now you are knowing. B is equal to Km divided by capital M. Then M is equal to what? Very just cross multiplication you can do. M is equal to K M divided by V. M divided by V. And M upon V, what is the M upon V? That is the density. Mass by volume is called density. Hence, now directly you can know M is equal to K into D. From this formula, what we have calculated, V is equal to K upon small m divided by capital M. From that you got the value of capital M, means molecular mass is equal to K into M divided by V, that is a mass by volume, that is called density. Hence molecular mass is equal to K into density. Okay, very easily you got the new relation, molecular mass and density relation. Here a small d, here a small d is the density, here d is the density of the gas. We can conclude from this equation what I told you now, that is a m is equal to kd, that the density of a gas is directly proportional to its molecular mass. More the molecular mass, more the density, less the molecular mass, less the density. A gas that follow Boyle's law, Charles' law and Avogadro law strictly is called an ideal gas. Again important things. A gas that follow Boyle's law, Charles' law and Avogadro law strictly is called an ideal gas. Such a gas is hypothetical, imaginary. It is assumed that intermolecular forces are not present between the molecular of an ideal gas. Real gases follow these law only under certain specific condition. Actually real gases don't follow the ideal gases, and if they are following, the real gases follow these laws only under certain specific condition, when forces of interaction are particularly negligible. In all other situations, these deviate from ideal behavior. Okay. Now I am going to tell about the ideal gas equation. It is very easy to derive ideal gas equation. We know three laws. That three laws means we are knowing Boyle's law, Charles' law, Avogadro law. And then now by using these three laws, you can calculate you can derive the ideal gas equation. Ideal gas equation is very, very important, and its concept we will use in solving the many numericals. Then how? Then Boyle's law, you know, V is directly proportional to 1 by P. Charles' law, V is directly proportional to capital T, means temperature, absolute temperature. And third, V is directly proportional to N, that is Avogadro law. Then all three laws are related to V only. V is proportional to 1 upon P, Boyle's law. V is directly proportional to absolute temperature, Charles' law, and V is directly proportional to N, Avogadro's law. If you will combine all three gases, then easily you can write V is proportional to Nt upon P, because only in one equation now all three are present. V is proportional to Nt upon P means what? It is telling first V is directly proportional to N, Avogadro's law. Again P is down, Nt upon P, then P is down, it means 1 upon P, hence Boyle's law is present. And T is up, then V is directly proportional to T, it means Charles' law is present. Then this equation V is directly proportional to Nt, T is capital, Nt, N is a small, divided by P. This relation is called ideal gas equation. But now you can simplify it. Proportional sign is there. Now you can convert into equality. Then that time you have to multiply by a constant. Then here constant is R, capital R. Where R is proportionality constant, and this R actually is called universal gas constant. Then see, now you got V is equal to R NT divided by P. Then just by cross multiplication, you can write PV is equal to nRT. Simple way. PV is equal to nRT, cross multiplication. PV is equal to nRT. This is also called, you can say, ideal gas equation. Another way to tell the ideal gas equation, PV is equal to nRT. It is popularly known as ideal gas equation, and this formula is commonly it is known PV is equal to nRT. Okay, R is called gas constant. It is the same for all gases. It has same value for all gases. Therefore, it is called universal gas constant. Then this equation, that is the PV is equal to nRT, is called ideal gas equation. Okay. Now you can get the different value of R. Okay. If you will put the, you can say, suppose you want to know the value of R, then PV is equal to nRT, then R is equal to what? PV divided by NT. Simple. PV is equal to nRT, then R is equal to PV divided by NT. R is equal to PV divided by NT. If you want to know the value of R, capital R, universal gas constant, then put the value of pressure, volume, N means number of moles, T means temperature. Then here, if you put the value of pressure like 10 to the power 5 Pascal, and volume, if you will consider 22.71 into 10 to the power minus 3 cubic meter, means m power 3. This is the volume. 22.71 into 10 to the power minus 3 m3, m power 3, that is the cubic meter, divided by n. N is equal to 1 mole. N is equal to 1. And T is equal to, already I told you, 273, or exactly you can write 273.15 K. Then after solving this, you will get the R value. Then now I am telling R value, that it will come 8.314 Pascal cubic meter per Kelvin per mole. Why it is 4 unit? 4 units are attached there. Then you have used 10 to the power 5 Pascal. Then that will be in the formula, last result, Pascal. You have written cubic meter, 10 to the power minus 3 meter power 3, that meter is present here. And Kelvin you have used, Kelvin was down, that's why per Kelvin. And mole was also down, 1 mole, that's why per mole. Then R, one result is 8.314 Pascal meter cube per Kelvin per mole. R1 result, R is equal to this. Second also, same result you can write in other unit. Then 8 point, you can write R is equal to also 8.314. In the place of Pascal, now you write bar. Pascal term you can write in bar. Then if you want to convert Pascal into bar, then you have to write 10 to the power minus 2 bar. And same time you have to write this cubic meter was there. In the place of cubic meter, you can write liter. You know that 1000 milliliter, that is equal to 1 liter. Then similarly 1000 liter is equal to 1 cubic meter, you know. Then now in the term of var, also you can tell the result R. Then 8.314 into 10 to the power minus 2 bar liter, and per Kelvin per mole will be as it is. This is the second form of R. R can you can tell. Now two form I told you. R can you tell in two value I told you, and third value also you can tell in third way. R you can tell in three ways. Two ways I told you. Third way, 8.314 joule per Kelvin per mole. Now here you can see Kelvin per mole is constant in all three forms. In all three ways, per Kelvin per mole is common. Then what is changing? In the first form, you told in the Pascal term, Pascal cubic meter. Second, you told bar liter. Liter you have simply written because cubic meter was there, you can write liter. 10 to the power minus 2 bar extra you have added. 8.314 is common in all three. And third, actually 10 to the power minus 3 bar liter, that is called 1 joule. 10 to the power minus 2 bar liter, that is called 1 joule. Hence, you can write in the place of 10 to the power minus 2 bar liter, you can write J, joule. Hence, you will get 8.314 joule per Kelvin per mole. This I told about the R, value of R, that is the universal gas constant value. At STP condition used earlier when 22.4 liter we were telling that time, at STP condition used earlier 0 degree centigrade and 1 atmospheric pressure, and value of R is that time when we were telling V is equal to 22.4 liter that time. Now it is changed. And now R value, if we will consider, earlier STP was 0 degree centigrade temperature and 1 atmospheric pressure, 1 atm, and value of R was that time 8.20578 into 10 to the power minus 2 liter atmospheric pressure per Kelvin per mole. That time earlier 8.20578 into 10 to the power minus 2 liter atmosphere. Here you are, now you are writing bar liter. That time it was called 10 to the power atmospheric liter per Kelvin per mole. That time also it was there. Just simply I am telling you, should not confuse. Okay. Ideal gas equation is a relation between four variables. Already PV is equal to nRT. Then total 5 term is there including N. Then ideal gas equation is a relation between four variables and it describes the state of any gas. Therefore, it is also called equation of state. N actually is common 1 mole, generally 1 mole. Then four variables are there. Then now this also we can tell PV is equal to nRT. In another way also you can tell. Suppose pressure is changing, volume is changing. Then what will you tell? Suppose pressure is changing from P1 to P2. Volume is changing from V1 to V2. Then here you know that nRT is a constant. N value will be fixed, R value is fixed, T value may be fixed. Then but pressure may change, volume may change. In that situation, that if pressure is changing to P1 to P2, V1 is changing to V1 to V2, and suppose temperature is also changing, suppose T1 to T2, then three variables are changing. Okay, then in that situation you can write P1 V1 upon T1. Actually PV is equal to nRT. Then nR is equal to what? PV upon T. PV is equal to nRT. Then T is equal to what? PV upon nR. PV upon nR. This is actually gas law, I told you, but pressure, volume and temperature is changing from P1 to P2, V1 to V2, T1 to T2. Then in that situation you can write P1 V1 upon T1, that is equal to nR. And again, if pressure is P2, volume is T2, temperature is T2, then that time you can write P2 V2 upon T2, that is again nR. Then nR is equal, both side nR is coming. P1 V1 upon T1 is equal to nR, and P2 V2 upon T2 is equal to again nR. Then you can combine both. Then you can write P1 V1 upon T1 is equal to P2 V2 upon T2. This is called combined gas law, and this is very, very important, and it is used in solving the numericals when temperature, pressure, volume during the reaction if it is changing, and that time this relation is used. Now I am stopping only here. Next class again we will meet. Thank you.